time domain perspective will help us in understanding what is happening in the L or C or the RL combination or RC combination and so. So we'll try to see what is it, that's the target, and then in time domain, how is the reactive power, that is the objective, not in phasor domain in general. And then we'll try to answer how the plus Q, minus Q, and so happens to be there and so. So that's the general agenda of this. So when I teach in class, or you teach in class, we do the same thing. So let me start from there, and then because that is also associated with time domain waveforms, voltage, current, and so. So let us say this V and this supplied by this source, and we have a resistance. So current flows V upon I. The power which is associated with this power is instantaneous power. So V into I. So if I say V equals to Vm sin omega t, so in this case, this will be Vm Im sin square omega t. So this leads to, as you know, a clear derivation on we can say that these are textbook things, so I'm not going about that. So this leads to two parts. One is a DC part, this is a DC part, fixed part, Vm Im by root 2. So that comes to be Vi in terms of that. And this you can say that the oscillating part or sinusoidally alternating part, but it has double frequency. It has double frequency. So average over a cycle 0 to 2 pi, this will give you 0, but this DC part remains. So that's you can say that we call it the average power or watt power, and that becomes equals to V into I. So this is a resistive circuit that comes from V into I. So in a plot waveform, V and I, if this is red is V, blue is I, then green one is P. This P is the instantaneous PT, instantaneous power, VI, product of VI at each instant of time. At each instant of time, if you plot, then this gives plot like this. So you know this on all books are available. So what it shows, the conclusion here is that this is a double frequency part. Over a DC, it is superimposed with the double frequency, and then this PT value is, however, is always positive. Why it is positive? Because current flowing in this direction or current flowing in this direction, positive half, negative half, whatever it may be, the corresponding things is that always the corresponding resistance consumes power, energy. So it flows this way or that way, it will consume energy, I square R, loss will be there in that resistance. So that's the reason the corresponding power, instantaneous power also comes to be positive in terms of that. Another conclusion we see here, that this is our load resistance. So this is power flowing into this resistance P, T, small t, small p, and that is coming from this source. So whatever is taken by the resistance is also coming to the source. So that's about the PT in terms of that. Now let us go to that. We'll go for that more and more. Oh, I don't know. People are numbering this. Now going to the inductance, what you do similar to that. So P equals to Vi, and here we talk about Vm Im sin omega t minus pi by 2. We know inductance, current lags the voltage by 90 degree. So pure inductive case. So that's the reason that comes from LDI by dt and so. Now I'm not going to that. So here what happens, V and current lags by, I can say that 90 degree. So this is this. So the product of this is nothing but this P, small p. So that becomes equals to the green one if you see here. So what we see here is that this product, when it happens to be, that gives, you can say that the general derivation of minus Vm Im by 2 sin 2 omega t. Unlike in case of resistance, a DC part and a double frequency part, here only double frequency part is there. So that means that this average over a 2 pi considered will be definitely 0. True. Now what happens here is that we see here this green one, which is our context here, is having a negative here and then a positive here, negative here, a positive here. This is within 2 pi, that is 1 cycle here. This is within 2 pi hour, 1 cycle here. 1 positive, 1 negative, 1 positive, 1 negative. So that's the double frequency. That's the double frequency. And also if you notice here, in case of your resistance is also average over this is our average power Vi. Over this, you can say that this corresponds to eventually 4 half cycles. So that's the double frequency oscillation. So power happens to be a double frequency oscillation. But in this case, it happens to be 0. Here we say here, that earlier in case of resistance, only resistance, we talk the P to be only in the positive half, not in the negative, but here it has both positive and negative half. Most of the things known, just I am to start with, I am repeating it. Now the case of the inductance. So what we say here, that the positive PT, as I already mentioned, that resistance case, the resistive circuit only takes positive perspective. So therefore, the PT becomes positive when the load consumes power. So what if it that perspective? So this positive, because we are talking about source is connected to inductance. So whatever positive we can say that power PT happens to be there, that is taken by the load. This is our load. Inductance is a load in this case. It implies that the negative one is nothing but power coming from load to the source side, load to the source side. With that argument, with that logic, which comes to be true, because I told you in case of resistance, it happens to be only positive. So negatively implies the corresponding system, in this case, inductive system, is giving back to the system. In a cycle, it takes 2 times. In a cycle, this is 2 pi. It takes 2 times, positive half 2 times, and gives also 2 times. It takes 2 times and gives also 2 times. And from this symmetry, we know we can say that whatever you consider in the positive, whatever it takes, it also gives same amount. And that's the reason the average value happens to be 0. And then this is not it does not have any watt power or average power in that respect. In a similar argument, we can say that logic, when the capacitor happens to be there, so this is the load here in this case. Now what we see here, same P equals to VI, but we talk about plus pi by 2, and this also happens to be a double frequency power. That's true. So that's why average power is 0, 0. That's true. So what we see here, that
Hello?
in this,
Sir, I think you have muted.
hello. Yeah. So in this case, what we see, that P into this is V, this is I. So this is positive, this is positive, this is negative, this is negative. Again, in the 2 pi, we have two positive halves and 2 negative halves. So that implies, again, you can say that this is power taken by this load, and this is power given back to the system, given back to the source, you can say that in this case by the capacitor to the voltage source. So that's the conclusion, and average power happens to be 0. So that's the about the PT what we say. Now what we say, if both L and C are there, what happens to we see? So both will having same voltage. So this will take some current, this will take some current. So they are operating in parallel. So if we say only L, as we have seen earlier, so what we say here, this is green one is PL, and the green one is considered in the below diagram is for the PC, the capacitor, whatever it takes. So what we say here, that within this 0 to 2 pi, there is a negative half in this first 1/4 of this cycle for L, whereas you can say that positive half, you can say that positive, you can say that P in case of 1/4 of the cycle. That implies that when the inductor is giving back to the system, the capacitor is taking power from the system. And similarly, next 1/4 cycle, whatever you can say that we say, when the inductor is taking power from the system, the capacitor is giving back to the systems. So that is what the genesis of here. So in general, we say that suppose I take a case of, for our understanding, QL equals to QC. So far, whatever understanding we have, QL equals to QC when have XL equals to XC, as you know. So it means that at any instant, if you see this, at any instant, if QL and QC are same, then at any instance, the PLT equals the P at L, P for L equals to minus of PC. So what I like to say here, that any instantaneous value of PLC equals to minus of PLT. So what the for L, when it takes something 1 unit, at that time the C gives back to the system 1 unit if XL equals to XC. That is what they are in. We can call it the PT of L and PT of C are in phase opposition, 180 degree apart. So so therefore, when both are present in this, the effective Q, that becomes equals to 0. And that's the reason, that is the starting point of when you say Q and minus Q. So we say QL and QC. Why plus Q for plus Q is that Q for L, minus Q for C will come to later on. But here we see here that because they are in phase opposition always, so therefore if one is plus, the other is minus in terms of that. This is the starting point for PC. Because we know This P, there is no real power. Even if you are talking about small P means instantaneous power, but here you don't have any real power, P average power or watt power. Everything is in terms of reactive power. So that means that at each instant, whatever QL happens to be there, there will be countering, you can say that QC for that. Now that is over. That is your background. Now let us come to an RL circuit. So we'll describe henceforth about an RL circuit. We can extend this idea to the RC circuit also. So for this RL circuit, if this is voltage, this is current, blue one is current, so it lags by an angle of phi. This phi depends upon the R by L ratio, L by R ratio, whatever you call it. Agree? So if phi becomes more and more when L becomes more and more as compared to R. If given a fixed value of R, if L is increased, phi increases, that we know. So our discussion here will be confined to only 0 to 2 pi. So what happens here? So you see here, when I make the product of V and I got to consider the corresponding plot to be considered V into I. So I got the plot to be like this. So what we say here, this is nothing but our PT, which we were earlier discussing. So we'll continue with only small PT, the instantaneous power PT. So earlier in case of L and C, we saw that the PT becomes positive half, negative half become same. But in case of here, it is not so. The phi is small, phi large, depends upon. So we'll say that ideal case also either only L, either C also, later on you can say, we'll go to that. So what happens that as per our, you can say that book things, this is taken from a book also, the average power comes out to be somewhere here, because you see here this positive half is much larger than the negative half. The positive half is much larger than negative half. So average over one cycle or average over half cycle here, because of the symmetry, that becomes equals to nothing but the P average, or that is nothing but your watt power or so. So what we say here, if this positive is nothing but taken from the source, because I said from the argument that R case only positive happens to be there, if this is taken from the source, this is nothing but given to the source side. That is given to the source side. So, so now the question is that if who is giving this? This is given by the inductor, because R case we say everything is positive. In L and C case we found something negative. So who is responsible here? The L, or you can say that C, the responsible for the they are the storing element. That's where they are able to push power to the consider to the source also. So let us see. We will have more details about this PT waveform throughout this discussion. So we say B equals to Vm sin omega t, I equals to M sin omega t, product B equals to Vm sin omega t. These are P that we like you are focusing here, and that becomes, if I extend this, P average becomes equals to Vi cos phi. In phasor domain, that comes out to Vi cos phi, where phi is the angle of the corresponding impedance. That is nothing but the impedance angle. We'll come to that. So the remarks, what we say here, that the small negativity here, this small negativity here from 0 to, this is nothing but 0 to 5 up to the 0 to 5, that the circuit is giving back to the systems, and in the positivity, the combination is taking from the systems. If this combination is there, so this load is taking from the source, PT, positive, when in this half, and negative PT means it is giving back to the system in the small period of time here, as shown in the diagram from 0 to 5. So that can be also, if we extend this idea to RC also, we'll coming to the same P average Vi cos phi. Why is same? Why the relation is same? Because in both the cases, whether it is RL or RC, who consumes the power? It is the R resistance consumes the power. So this you can say that I square R always happens to be there. This is equals to nothing but your Vi cos phi, and this is nothing but your P average, or the watt power or kilowatt power. So that's the generic case. The power is consumed by only and only R. L and C are, they are not power consumer. They only can store and again give back to the system. So that's the conclusion. R is the only factor that consumes power, and minus PT is coming, negative PT is coming only due to because of the presence of L or R or both. So from this one, I go back to this something more. So this point is nothing but the 0 to 5 point. We'll see. So the energy, the area under this core, on this portion, small area, which is nothing but given back to the system side, negative P, because positive P is nothing but consumed by this, taken by the corresponding load. So in that case, the negative one is the taken by the negative one is given by this L and C. So it must be the L and C must take amount of energy from the positive half. So when it goes to the positive half, so they must store charge. The inductor gets energized half Li square, half Cv square, and so. And that storing business happens to be there, or energy you can say that storing business happens to be there in the positive half, and the negative half, the negative part you can say that not half, the negative part they give back to the system. That is our understanding in terms of that. So when only an LMC present in the circuit, this sum of power becomes equals to 0. The total sum of power over, you can say that the you can say that 2 pi becomes 0, that we know. Okay. Now let us we analyze the corresponding waveform in terms of the, some algebraic analysis and so. So this is the same curve. So this length is nothing but 0 to 5, because Vi product, this is nothing but Vi product. So I lagging behind V by phi. So I0 at phi angle with respect to voltage. So I0 is 0 and V0 is 0. So V or I, anyone is 0 means the corresponding this 0. So let's see, this point is 0 due to that, and this point is 0 due to voltage 0, and this point is 0 due to again current 0, and like that. This is about the PT. So V equals to Vm sin theta, omega t equals to theta I have taken for the derivation, and I equals to Im theta minus phi. So this is theta equals to omega t. So that we convert to theta is the variable here. So Vi becomes equals to this, that is the derivation, and then this Vi product becomes this. So I can have two parts, you can say that from this. So this sin theta cos theta, this part, this becomes this. So I can extend this. So my purpose here is to integrate during this period of 0 to 5. This small period where the energy is given back to the system, that period of things we like to observe right now first. So this integration from 0 to 5 for this Vi d theta, theta is, I taken theta equals to omega t. So I like to see this integration, and then we see this integration that comes out to be in terms of the area 0 to 5 comes out to be Vi phi cos phi minus Vi sin phi. This area comes out to be Vi cos phi minus Vi sin phi. See this, the area under this small portion happens to be Vi phi cos phi minus Vi sin phi. So we know this Vi cos phi is nothing but I square r, and Vi sin phi is nothing but I square x. So therefore Vi cos phi, you can say that it becomes phi I square r phi minus I square x. So this term we see here, this term as we see analogous to this, that the resistance consumes power I square r. That is the average power, you know, already seen earlier, and this corresponding energy, which is capability of this associated the inductor, is nothing but I square x. Note that this is area, so this is only energy. This is nothing. There is no power here. So therefore, what happens that because this is I square r is the power, and the width of this one is phi. Phi is again some angle, so that happens to be omega into t kind of thing. So this phi into this I square r into phi is nothing but coming this first part. But here there is no phi, nothing. It is straightforward I square x. See that this I square x is nothing but also general the Q reactive power we call it. The reactive power we call it I square x. So that will like to explore what it happens to be there. So there are two terms in this area under this is the Vi phi cos phi minus Vi sin phi. In the second term, there is nothing multiplied by phi. Both are having cos phi and sin phi. So we know that one is real part and the other is imaginary part kind of thing. That's I square x, I square r part. But here in the real part perspective, the r part perspective rather, is phi is multiplied. There phi is not multiplied. So what do you mean by this? In this period of 0 to 5, that is what we are discussing. So if we consider this I square phi minus this area of this one. What is this area? This area we are considering only nothing but this corresponding Vi product across the load. We are only considering that of the load. So this load takes or interacts power with the source. So therefore I say that energy received by the source, because now it is minus, you can say that PT, So energy we receive by this source is nothing but this area under this curve. This is what the, because negative area. So this is nothing but, however, comes out to be in our derivation I square r phi minus I square x. So this r component is nothing but comes out to be energy expended in the r, and the this part you can say the energy given by the inductor. So you see here I square x is negative. What does it mean? Because we say that everything is positive is nothing but taken from the source, and everything in negative p is nothing but given to the source. So this part is nothing but given by this inductor. This part is given by the inductor. This part is consumed in the resistor, and that will multiply 5. We'll tell about that. And that's the part, and the rest part is nothing but goes to the source. So when you see from this explanation, what you see that whatever the inductor gives, because it is giving, so this acts as the source now, and this acts as the corresponding sink, or you can say that load. In this path, the current is delivered to this through this one. So therefore, the resistance consumes now also. Resistance anyway will consume whatever path the corresponding, whatever way the corresponding current flows. This will consume again, and this will, you can say that is also non-consuming because the negative power happens to be there. So this source here acts as this part, and this become your sink, and this become your resistance that consumes power in terms of that. So all positive terms are nothing but consumption, negative term is nothing but the generation in that case. When you look from the load side, this I square x is nothing but we call it power in case of that, so called Q equals to I square x, reactive power you call. But this I square x here in this from the 0 to pi period is coming not a power, it's coming as an energy. Agree? And this I square r phi, I square r phi first term is from 0 to pi power. So divided by this, the power, if you take the average power divided by phi, this is energy period of 0 to pi. So this energy divided by this pi is nothing but the average power rate of energy associated with r. So that becomes equals to I square r. So that means that within that small period also 0 to pi, the average power associated with the average power consumption by this r is nothing but I square r also. So that is true. So the rest part is nothing but associated with the reactance. So in conclusion, we said that another thing I will point out here, that in the next portion we see that this I square x is nothing but provided by this inductor, so that must be received in the positive half. So the inductor receives I square x and gives back I square x over. But when the inductor gives back to the system I square x, in that path, the resistance comes into picture. And this resistance is nothing but consumes also that time. So when L is giving power, energy, the resistance comes into path, and some energy is expended in the R. So the rest of the energy is received by the received by the source. So source gives in the positive half power and energy to both R and L. So in that process, R also consumes. L stores its energy, but the negative half L only gives, R again consumes, and so also the source. That implies that the source what has given to the inductor I square x, that I square x does not fully come to the source because the resistance. So that's the lossy part, and that's the reason we talk about in the presence of inductor there will be associated losses. That if you increase more and more Q because of the L iron high, phi increases, and your corresponding I square R loss in the system also more and more. I square R phi, that will also go on increasing. Now come, yeah, we are still describing this. So let me say, consider what this equation reveals further more little bit. So this is Vi, the 0 to phi integration, this area only, the small area, that equals to Vi phi cos phi, Vi sin phi, that equals to, we call it as I square R phi, as far if we derive that way, I square R phi, I square X. So when the circuit is only resistive, so phi equals to 0, we like to validate this corresponding equation. So that time the area under Vi, this phi 0, so this area there is no negative part in case of resistive things, only positive half, so this becomes 0. That's true. That comes from here also. You see your phi 0 and sin phi 0, that also 0, 0 minus 0 becomes 0. When it is only capacity, phi is now minus 90 degree. So that means that the Vi minus pi by 2, that becomes equals to Vi. So when it is pi by 2, so if we substitute here pi by 2, and then this is pi is 0, this part is 0, and then only is pi by 2, so that becomes equals to Vi. When this is only capacity, pi is minus 90. When it is only inductive, pi is plus 90 degree, and then this Vi, so if you see this here, this comes out to be minus Vi. So for capacitance, it comes out to be plus Vi, and for inductance, it comes out minus Vi. So that's the reason of we talk about the plus Q and minus Q as we are arguing earlier also. So that's the point here. We see here for inductor and capacitor in the 0 to pi. This is 0 to pi only. In this case, this becomes negative, this becomes positive. So plus Vi minus Vi is coming here. If you go by an intermediate point, let us say pi equal to 45 degree when r equals to x, so that becomes equals to the corresponding area, that becomes equals to minus 0.152 Vi. So that kind of situation happens to be here. Here it is minus. That minus means the inductor is able to give some energy to the system as a system back. So this area is nothing but we call the minus s square x, this part, the minus s square this. So what is coming back to the source? This is coming back to the source is nothing but this amount, I square x, and then you can say that minus Vi phi cos phi will be that part. That part will be coming back to the system in terms of that. Now come to the rest question. So we now discuss about this part, the small part. Now we go to the positive part in an RL combination. Again, we are discussing about RL combination. Now we are talking about phi to pi. So in phi to pi, what we say here, that becomes equals to Vi d theta, and this becomes equal to Vm Im, same kind of equations what we say in general. So we are looking now from the corresponding area under phi to pi, area under phi to pi. So energy during this period. Area means you can say that energy, and it is individual point Pt is nothing but instantaneous power, volt ampere. Average power is watt, and reactive power is var. So here we are talking about the energy because the integration of our period of time of the Pt. So this energy, we have two parts here, and this energy, if we go from the this part during phi to pi, oh, some part is deleted here, I don't know. Okay, somehow it is missing here in this slide. Let me check. So for that case, we'll get equation. Yes, let me say here. So this corresponding equation becomes equals to Vi pi minus phi cos phi Vi sin phi. Vi pi minus phi cos phi Vi sin phi. So what is Vi sin phi? Again, it boils down to I square x. And what is this? This is nothing but I square r into pi minus phi. So this is the integration from you can say that from pi to this. So let me say here, then it will be better. You can say that. I don't know how to address that. Somehow in the PDF conversion I'm missing it. This is slide number 13. What happened like that? Pi to pi. Okay, let me see. I don't know. Somehow I omitted that in the last moment. So this comes out to be in the integration process I square r phi to pi, and this comes out to be I square x. Note that in earlier case we are getting minus I square x, and this we are getting I square r pi. So here you can say that this part is nothing but we are talking about phi to pi. So that leads to, you can say that here earlier case we are talking about 0 to pi. So there it was coming minus I square, here it is coming I square x. It means that the inductor is taking power here, it is positive power. But here, see here, the resistor is again taking power, positive, that's true. But the product, the corresponding integral is now pi minus pi, because this duration from here is nothing but pi minus, this is pi to consider pi minus pi from A to B. So therefore, if you say that average power here also, I square R, P average here also, I square R, pi minus pi divided by pi minus pi. So this P average again is written as I square R. So what we say here, that in this positive half, I square x is taken by the inductor, and the corresponding resistors takes I square R pi minus pi. So I square R pi minus pi is the consumption by the inductor, and then I square x is the corresponding power. I square x is the power, corresponding power taken by the inductor or the capacitor in terms of inductor in this case. Now let us say the power analysis during 0 to pi half cycle, what happens? We add both 0 to pi and pi to pi half cycle period. So 0 to 0 degree to this, we got this bi cos pi, bi phi cos pi minus bi sin pi, and in case of here, the second part 0 to pi this we got this to be bi pi minus pi and corresponding bi sin pi. So this becomes equals to, total becomes equals to bi cos pi pi. So this the energy over 0 to pi. So we divide by pi will be nothing but the bi cos pi. So that is nothing but your I square R. So again this P average maintained in this case. So that's true. So the P average becomes this equals to I square R, that we see. Now we see that what happens, what is the reason behind this? If you see this curve, this is V, this is I for an RL circuit, and the phi, the corresponding current is lagging by a phi angle. This is V0. So when V0, this V0, what does it mean? This means that the power associated the source is V into I is 0. V0, I0. But what we say here, that at V equals to 0, I is negative. So what we say here, so therefore the I square R for the resistance, even though V is 0, is no more negative, it has to be positive. I square R consumes power at t equals to 0, V equals to 0, I is not equals to 0. So resistance consumes power. What happens to L? PL is VLIL, but your VL is nothing but LDI by dt, so into I. So it is both resistance and inductance are dependent on the corresponding current. However, the current is governed by the voltage, but you see here what happens that nowhere V term is there. So both are dependent upon this corresponding current. I square R will be there because I is non-zero at t equals to 0. So at V equals to 0, V equals to LDI by dt. So therefore PL not equals to 0, because neither I is 0, neither the di by dt is 0. Di by dt is positive here, because if you see this trend here, the di by dt becomes positive here, so it is giving energy at this point. I is negative, di by dt is positive, so that's why this factor comes out to be negative, and that is what we found in our earlier discussion also. So what happens here, that if you see this perspective, what is the reason? So at this point, the power here is 0, but the resistance consumes power, inductance gives power. So the power sent back by the inductor, it's consumed by the resistors, and this becomes 0. So what we say here is that the inductor now at this time the corresponding source acts as a short circuit, because V is 0. So therefore, if we short it, only the inductor is supplying the corresponding power or energy, and the resistor is consumed everything at V equals to 0 only. Now see only L here. So if you see this only L here in the RL circuit, so the VL equals to this, and the power equals to I LDI by dt. So this becomes this, and this PT comes out to be I square X double frequency power 2 omega t minus pi. So this is only inductor in the RL circuit. And if you plot this, then this becomes equals to the corresponding PT becomes equals to, see here, when it happens to be 0, voltage 0, T0, the power here starts from here, and that factor comes out to be I square X 2 sine omega t minus phi. We'll talk about that at this point. What is the power? And when the corresponding V happens to be peak pi by 2, you see here the corresponding this power also, the inductor power is this. The thick curve is for the only, you can say that inductor power only, V and I are there. So to analyze this further, this inductor power, instantaneous power every throughout, we talk about VL at t equals to 0 is nothing conservative minus s square x sine 2 pi. This power. At t equals to pi, at this point, it becomes 0. Because at this point, I is 0, so the I into L dt, that becomes 0. True. Omega t equals to pi by 2, at the midpoint, this becomes equals to this point, and we substitute here, you can say that comes out to be I square x sine 2 of this. And further, at when the correct becomes peak, derivative of that becomes 0. So therefore, you can say that at pi by 2 plus pi, this becomes again 0. This becomes again 0. At pi, I can say that again it follows the corresponding PL equals to 0. So therefore, we see here, inductor in the RL circuit again oscillates in positive and negative, same thing, and therefore it does not consume or does not, as a average, you can say that average power happens to be 0. Once it takes power from the source, the other half you can say that it energy, so that it gives back energy to the system. Now only with R, so this is I square R, and the PRT in this period, you can say that the whole in general formula takes as I square R equals to I 1 minus cos 2 omega t minus phi. So at different points, you see here, first point at t equals to 0, this also I square R, you can say that is this. But you see here, this power becomes 0 when I equals to 0. And then you can say that here, the corresponding I again happens to be 0, so that time it will be 0. So in resistance case, power becomes 0 only because the I square R, that the corresponding power becomes 0 only when I equals to 0 in that perspective. So that's the about different points. You can say that point also we can find the corresponding power relation for the resistance also. So in the combinations in the RL circuit, the PL behaves like this and the PR behaves like this. Let us say at t equals to 0. As I said, V equals to 0 and the power supplied from the source is 0 because it is short circuit equals to 0. So L gives minus I square x sine 2 pi and R takes I square R cos 2 pi. This is the power, you can say that handled given by the L because the negative power at 0 we have already seen, and R takes, you can say that I square R 1 minus cos 2 pi. So if we add these two, and then you can say that you know this relation R, X, Z, phi, from where you get the relation, then it comes out to be 0. So this power with L, and this becomes 0 at t equals to 0. And as I told, at that time V is nothing but a short circuit because V happens to be 0. So therefore, V neither gives nor takes power at that time. So these are the two plots, P of L and P of R here. So these are, you see here, they are relations. PR is always positive and this is plus minus like this. And again, you see this part, initial part here, initial part here also. So that's the perspective and so. Now, we'll just go back to these phasors because many students are also here perhaps. So let us say RL. So for RL, if you see here, we draw the phasor diagram. What? We draw the phasor diagram VR, I into R. This is I, the reference, I into R, VR equals to IR. VL, JIX, J into IX, VL, because we know current leads by 90 degree. So this becomes VL. So this becomes your supply voltage VS. If we divide everything by I phasor, this boils down to R, XL, Z. This is the phi. What is phi? Phi nothing but the corresponding angle between voltage and current. Who governs? The impedance. So this comes from the nothing but the corresponding Z phi. So this angle of the impedance is nothing but the corresponding this angle and this. Now if you see this perspective, this Vs here, the I, so in phase component, Vi cos phi, and the corresponding perpendicular component Vi sin phi is nothing but your Q. So far that we know. What to derive there also, I similar line, agree? And in case of this, you see here, in case of C, current leads voltage. If current is a reference here, because combinations, this IR, voltage lags. So this is BC minus of JXC because with minus JXC. So you divide everything by I. So it reaches to R XC minus XC and then this corresponding phi. You can take it minus phi also. So Z here is nothing but Z minus phi because R minus JX C. So this comes out to a J minus phi. So therefore we say here this in the phasor domain you can say that we talk about I leads the corresponding VS by this. So what we say here that in this both the perspective that if we talk about the impedance triangle, the R XL Z, R minus XC Z, so this comes out to be Z phi and this comes out to Z minus phi. We'll come to that. So if you go for this complex power, I'm not going to the definition. So this comes out to a VI conjugate. So this V equals to phi V equals to this. So S becomes equals to VI conjugate, that becomes equal to the phi. And again, this phi is nothing but, as I said, comes out from this Z of angle phi. Because I lacks voltage by the angle phi, that depends upon the Rx combination and so on. So we talk about this is just VI cos phi, VI sin phi, and this becomes equals to PJQ. So from this derivation, we say this is what all books thinks. I'm not going to this phasor domain. Just I'll put some questions here to myself. S equals to VI conjugate. So that becomes equal to IZ conjugate this. So that V becomes equals to now the S becomes equals to this. So this comes out to be S becomes equals to V square by Z conjugate. If we take this perspective, that becomes much simpler. Those who are teaching, maybe this is my way of thinking. That if you take this S equals to V square, where V is nothing but the magnitude square, V phasor into V conjugate, that becomes V square. So divide by the Z conjugate, then we get the corresponding real to this, imaginary to this. So that becomes equals to, so in general we say S equals to I square Z, that becomes this, and in general we say this to be this. So what we say that Q equals to 0, it means resistive circuit, Z 0, Q is positive, Z positive. That is from here only, where from this relation I square Z or equals to B square divided by Z conjugate. S equals to I square Z, I is the magnitude square, and the Z, that is Z angle, straightforward, or V square divided by Z conjugate. So if we S equals to I square Z, so it means that Z has an angle phi. So with this magnitude, so S will also having the volt ampere, you can say that will be having also a phi angle. So this results in, you can say that, let us say phi is positive. So this results in corresponding P, and this results in Q, and this results in Q, and this results in phi. So if phi is positive, Q is positive. If phi is negative, Q is negative. This is straightforward. So if we go by that, then the corresponding calculation process becomes simpler in terms of that. So always use the corresponding S equals to VI conjugate. This becomes equals to I square Z, or this becomes equals to B square divided by Z conjugate. So this will give you the corresponding P plus JQ. If it comes to be Q positive, then it becomes inductive. It comes to be Q becomes negative. It is not like convention or so. This is totally from the Rx plane and so. So you see here, this is phi positive. The corresponding things becomes, if you go by the B square by Z conjugate or I square Z, then this gives on the corresponding power triangle becomes this. If you go by this corresponding RC circuit, the impedance triangle is this, the corresponding power triangle is this. So by this way, you consider you can find out this corresponding PQ in terms of this. Now come to the definition of this reactive power, what is there in the book. So I'm consume more time in terms of the presentation. So I square R, you know, that is active power. What is that? I square X Q is I square X. That becomes equals to, from the I square X, omega L I square. And that becomes equals to omega Im square. If we do, then becomes half. So we see here this half Li square formula, you know, half Li square. So at the peak value Im, so that becomes equals to half Lmi square. So Q is called peak rate of energy storage. Q is called the peak rate of energy storage. The reactive power is the peak rate of energy storage in the reactive elements of the circuit that we saw, what we analyzed earlier. The average rate of energy storage is 0, plus minus 0. The energy continually flow into the back out of the reactive power components. Q is a measure of the energy exchange between the source and the reactive part of the load. Q is a energy exchange between the source and the reactive part of the load. But what we saw is that this, when the exchange happens to be there in the negative half, we talk about minus I square X. but at that time the corresponding resistance takes I square R phi. So this is nothing but that goes to the source. So it's yes, it exchanges energy to the source, but by the way the corresponding resistance consumes, so the source receives less than the I square X. So we all are power. So how to teach? That is my way of seeing. So as I said here in the power triangle or from the impedance triangle, you can conclude this is P plus JQ or P plus minus JQ. So if you see here, whatever is flowing here goes to here. So this must consider this side also must be P plus JQ. If it is P1 plus JQ1, this also must be P1 minus P1 plus JQ1. Who is providing? Source is providing. So we studied our diagram from the resistance, inductance, capacitance, and so there also whatever is taken, there must be given. So therefore here is give and take kind of thing. So what you talk about here, 5 kVAr here, 5 kVAr there, minus 5 kVAr here, minus 5 kVAr there. Who provides synchronous machine, whatever source is there. And this synchronous machine has to operate such that it provides that 5 kVAr. It provides that minus 5 kVAr. It's not that it is going in an inductive mode or capacitive mode or so and so. That has to be given in terms of this. While teaching, we come across another things, so-called 2-watt meter method and so. Of course, 2-watt meter method is no more applied. This is a theoretical things. Today all digital meters are voltage, 3-phase voltages and currents they too. So it is like a theoretical thing. But still then in books there, many might be teaching and so. But still it can have some concept. You can say that single phase wattmeter, digital wattmeter you can put, and you can put questions also. Whatever it may be. So we see that the Q here happens to be here equals to root 3 W1 minus W2 for this arrangement. And the W1 happens to be 30 minus pi, W2 happens to be 30 plus pi, depending upon the connection, or it can exchange also. So the question have that wattmeter reading negative. So student this time also asked me, what do you mean by consider negative wattmeter? Wattmeter is wattage, power, this. Why it can be negative? We saw all in our derivations, when we talk about average power, which the wattmeter happens to gives. Power, wattmeter you consider gives is nothing but VI cos pi. So that must be considered a positive one. Then why it happens to be negative? See the relation here, as I say, the phi is positive for inductive circuits. So let us say any angle, whatever it may be, this becomes wattmeter 1 becomes 30 minus y, this becomes 30 plus pi. So as you know, in your book it is there, when phi becomes greater than 60 degree, so this becomes greater than 90 degree, this part becomes negative. So W2 will be here, in this case will be negative when the corresponding phi angle more than 60 degree and so. And this becomes still positive. So power given to the RL load or whatever load at that time will likely. So then W1 plus W2 still happens to be positive because W1 will be higher than W2 because this is cos term. True. Now why it becomes negative? You see here the phi goes from 0 value, resistive value, and goes on increasing and goes on increasing and still goes on increasing from greater than 60 degree. So when it becomes more and more inductive, it means Q is increasing more and more with respect to the P. So that's the reason we say that this Q is again flowing here, you can say in terms of the rho. So now how to answer that why this corresponding negative? Yes, the wattmeter reads negative. But what is an wattmeter? In digital domain, the wattmeter is nothing but voltage phasor, computes current phasor, finds the angle between them, just like relay, and then makes the corresponding calculation VI cos of phi. So it is voltage calculated, current calculated, VI cos phi calculated. Phi the angle between voltage and current. Whatever line voltage, whatever angle comes between that. So this, if you say today the digital wattmeter is nothing but a calculator. So whatever V and I happens to be and phi happens to be there, accordingly it happens. So therefore, just like calculator, whatever inputs you give, accordingly calculated value will come to this case. That's the about that this thing. And the negative thing is happening because of that rule of the Q here. If Q happens to be significantly higher than this because 60 degree more, then it happened. Now another question comes here, when this capacitive case phi becomes negative and this 30 minus phi, this will happen, 30 plus phi, they will exchange, W1 and W2 will exchange in this case from the relation perspective. That is what I like to say. So the conclusion here is that when you analyze this corresponding RL circuit or similar to the RC circuit, the power curve happens to be both positive and negative half. So negative, you can say that part. So in the negative part, it gives back energy to the system. In that process, we say that gives I square X that we saw. And then the reactive power stored in the inductor is I square X. Whatever I square X stored, that gives back in the system. To this source, it gives I square x minus I square phi. If phi is more and more, so then it can give more and more. If phi is smaller, it can give smaller and smaller. So that is what something about this. This is there is nothing like to conclude also. You can think of yourself and you consider explore more on this perspective also. Thank you.